This video is on van der Waals equation, and what van der Waals equation does is it adjusts Pivnert. So Pivnert assumes an idealized model of a gas. The problem is this, okay, two of the underlying assumptions of the ideal gas and kinetic molecular theory are not entirely true, particularly under certain circumstances, particularly at low temperatures and under conditions of high pressure. And these two variables that are important allow us to make adjustments to the equation. And these adjustments are specific to the gases. So van der Waals came up with two constants, an A, okay, and a B. And one of these two things deals with volume adjustment. Okay, because the assumption that the molecules of a gas take up no space in the container is not entirely true. At standard temperature and pressure, at a low pressure, the molecules do take up an insignificant amount of the space of the container. But if you have like a scuba tank or an aerosol, a can of propane, there's a lot of molecules in there, and they're literally taking up some of the space. And basically, that means you have a smaller volume. And we'll see that adjustment. The other volume has to do with IMFs. Okay, and the reason why you have to make an adjustment for that is the assumption of kinetic molecular theory is every collision is perfectly elastic. And molecules don't tend to stick to each other. So when you're describing, the gas in kinetic molecular theory, you're like, oh well, this is a gas. The particles take up almost no space, and they bang into the walls of the container, and they bang into each other, and there's a complete transfer of energy, and there's never a loss of energy. Well, the reality is when molecule A bangs into molecule B, or they're close to each other, they start sticking. And that's going to have an effect on this equation. So let's rewrite the equation with the adjustments. And watch where I put the adjustments and think about how they're going to affect the pressure. And the critical thing you want to recognize here is that in the AP exam, this formula is no longer on there. But I've seen in different places where they have the formula show up, and you need to understand it, but not necessarily do a calculation per se. So here's the adjustment. You have the pressure is equal to nRT. And on the bottom, you have V minus NB. So this is the first adjustment. This little minus NB on the bottom. Now, N is the number of moles, right? And B relates to the size of the molecule. So big molecules would have a large value of B, small molecules are small. So this literally B deals with, the mass of the molecules. And so you can assume that if you were dealing with like neon, this number would be pretty small. But if you're dealing with like UF6, UF6 is radium hexafluoride, which is used in centrifuges for separating out isotopes of uranium, so it's a very useful, important compound. The B value would be rather large here because these are big molecules. Uranium is a big, massive atom, and it's got 6 fluorines around. It's still a gas, but it's a big molecule. And so what you want to recognize is this. In this part of the equation right here, what I'm basically doing is saying the volume is smaller. And if the volume is smaller, okay, and this is something that doesn't change from what you learned in 10th grade. If you make the volume smaller, the pressure goes up. So if you're dealing with UF6 and you've got a large number of them in there, like a large number of moles, okay, what that means is the V is going to be less, and therefore the pressure is going to increase. So one of the adjustments causes an increase in pressure, and that's what the interesting thing is, because the other adjustment we're going to find does the opposite. So the other adjustment is here, minus A N over V squared. Now this has to do with basically the IMFs, or the stickiness of the molecules. And if the molecules are sticking to each other, it means they're losing kind of energy. They're not going to hit the walls with the same amount of force. So if you see this big negative here, okay, A, okay, deals with the IMFs, the stickiness of the molecules. And the fact that the molecules are sticky is going to cause them sort of like, basically, if this molecule A is pulling in another molecule, okay, then that molecule is not going to be banging against the wall of its container as often or as with as much force. So the interesting thing is the two balance each other out. And that's why under normal conditions, okay, you can kind of ignore them because one makes the pressure go up, that's B, and the other one, the stickiness, makes the pressure go down. In a lot of cases, they kind of cancel each other out. And what van der Waals did was he actually quantified. So you can look up the A and B values, plug these in, and find out what the pressure will be for that particular gas under any set of conditions. You're not going to have to do this. All you want to know is, okay, this one increases the pressure, and this over here decreases the pressure. And worst case scenario, you have to plug in a lot of numbers into a complex calculation. But you basically want to view this like as how pressure overall is affected by the molecules taking up some of the volume or the molecules not having perfectly elastic collisions.